Let's go back to this idea of areas. As we said, area under the curve, we can work out the integral. And we said if it was above the x-axis, we know the answer is positive. If it below, it was negative. But sometimes you might get a graph like this where it's a combination. So how do we handle it? So we've got some area below the x-axis. So fair enough, A to B, that's above, so area 1, I can just do the straight integral. That's going to be positive. But I'm going to have to break it up into two integrals. If I now want to work out, there we go, B to C. So if I was to work out the total area, I could not just go from A to C. Because the integral, if I did that, I'd substitute in the C, then I'd substitute in the A, but it would take away area 2 from area 1, and I wouldn't get the right answer. It'd be the right answer for the integral. So if it wasn't an area question, and we're using the integral for something else, fine, that value is fine. But for this sort of question, it's no good. So I have to break it up into two areas, the area above and the area below. And so to work out the area below from B to C, well, there's different ways I could work it out. I could simply say, oh, I know that's the negative from B to C. But other ways we saw, or I could say, oh, it's the absolute value from B to C. Or I could swap the limits round. Remember we said when we swap the limits round, it'll find the negative of the answer. So that's another way I could do it. So either one of those three will work. Probably the most common one is the top one, but I must admit the last one can be useful as well. The second one probably tends to come in when people are fudging their answer. So they do the area and they get a negative answer and they go, oh, area can't be negative. No worries. Absolute value, absolute value, absolute value, absolute value. And we get the answer. Okay. Now, we know this integral from -1 to 1 would be 0, because it's an odd function. Area below would cancel with area above. So if I simply do the integral, I get the answer of 0, and of course that's a ridiculous answer for the area. So I could break it up into below and above. So from -1 to 0, I know I'm below, so it'll be the negative of that, and above 0 to 1. And then the actual integrals are the same. When we integrate, the primitive function is still a quarter x to the 4. And we sub in and we get the actual answer of 1/2 units squared. Of course, the other way I could do that one is use the symmetry. I know the area below is equal to the area above. So I could have gone twice from 0 to 1 on this particular one. That's if it's symmetric. I could take advantage of that. And sure enough, we get the same answer. However you prefer to do it, really. Here I can't take advantage of symmetry. All right, so I've got this polynomial. I've got a bit above, I've got a bit below. So I'm going to break it up into two integrals. But as I say, it's the exact same integral that I'm doing, just the limits have changed. You'll notice this is where I've used the technique of, I'm going to swap the limits around and change the sign. So that second one, instead of having minus from -1 to 0, I've turned it plus 0 to -1. The advantage of doing that, have a look at the top values on both of these. They're -1. So I'm only going to substitute that in once, but multiply it by 2. That saves a little bit of time, I suppose. So I'm going to have 2 lots when I substitute in -1, and then it'll be minus the bottom ones. So minus when I substitute in -2, and minus when I substitute in 0. Well, of course, all of that becomes 0. What about if the area is going to the y-axis instead of the x-axis? So there's our random function, y equals function x. Going to need to know the y values as well to do this. We're going to have to make x the subject. And then we're going to sub in the y coordinate. So our integral, you'll notice, becomes gy dy. And the way to remember it is, if the area is to the x-axis, then it's dx. So we need it in terms of x. But if the area is to the y-axis, so we need it in terms of what we're integrating, so to y. So for example, there's y equals x to the power of 4. Yes, I know it looks suspiciously like x squared, but trust me, it's x to the 4. And we're going to find this particular green area there. Now I know the x values are 1 and 2, so in order to do this integral I'm going to have to work out the y values. And I'm going to have to rewrite the equation to make x the subject, so I've got it in terms of y. So x will be y to the power of a quarter. And so my integral will go from 1 to 16, the y values, y to the power of a quarter, dou y, because we're going to the y-axis. It's good, that. Add 1 to the power over the power, so turn the 5 on 4 upside down. In this case, I didn't bother writing that as y, what would it be? Y times the 4th root of y. Because I know, actually, I can find this as an exact value, because the 4th root of 16 is 2. So 2 to the power of 5, I know that works out neatly. And the final answer, 124 and 5. Well, what about if we trap an area between two curves? So random function number 1, random function number 2. And we want to find what area is trapped between these two curves. So in there. Okay. Well, the point of intersection will come in handy. So those x coordinates are A and B, we'll call them. And when I draw it like that, it's pretty clear to see what happens. We just got to basically find the area under the red curve and subtract the area under the blue curve. That'll give me the bit that's in between. So I guess it's important we know which function is on top. Because if I pick the wrong one, I'm going to get a negative value, but then we know what all you fudges will then go and do. Absolute value, absolute value, absolute value, and so on. There's our integral. Hey, but we're going from a to b in both of them, so I could actually make that one integral, function x minus g of x. Now you might be thinking, what happens if there's a bit below or a bit above? Doesn't matter for this one. Because I'm just finding the area between two curves, if I had a bit below and a bit above, I could shift the whole curve up, say, who cares, 1,000. And so this one would become function x plus 1,000. This one would become g of x plus 1,000. So both of them now are above. But when I subtract, I still get function x minus g of x. So it doesn't change, because the thousands end up cancelling. So we don't have to worry about what's above and what's below in this case if we're trapping between two curves. So we're going to find the area between x to the power of 5, y equals x, just in the positive quadrant. So there's y equals x. There's a very dodgy x to the power of 5. I just want this little bit in there. Okay. Got to find the point of intersection. That's pretty tricky. When does x to the power of 5 equal power of x? Better solve that. Okay. Oh, right, it's 1. 1. Who would have picked that one, eh? So, okay, we're doing the area. The blue one's on top. So x minus x to the 5. Add 1 to the power over the power. There's our answer, 1/3 units squared. Let's have a look at this HSC one. We've got a parabola and a line. Again, doesn't matter that it's below, because the area we're trying to find here is totally between two curves. So I can just do the top one minus the bottom one. And this was a 2-unit question, so they have been really helpful. The graph of x minus 4 and x squared minus 4x intersects at the point 4, 0, I think I've left a word out there, and A. So just in case you couldn't see that in the picture, they told us. Find the coordinates of A. Solve them simultaneously. Remember? X minus 4 equals x squared minus 4x. We get two answers. One answer is x equals 4, which we were expecting. The other answer obviously must be A. So A is the point 1, and its y value when we sub back in, -3. Remember? 2-unit questions. Find the area of the shaded region bounded. Okay. So top one minus the bottom one. Line minus the parabola. So I'm integrating -x squared plus 5x minus 4. Add 1 to the power over the power. Substitute in. And there we go, 9 on 2. This was an interesting one. A bit later in the paper, you'll notice it's a question 8, so there's probably a bit more happening. So we've got the circle, radius 2. We've got a parabola, x squared minus 3x plus 2. By considering, they've given us a hint, by considering the difference of two areas, find the area of the shaded region. Now here's the thing. If the boundaries change, you need a new integral. So up until we go from 0 to 1, I could go circle minus parabola. But once I go past 1, I can't do that anymore. It's now simply circle to the x-axis. 2 integrals. Mind you, that's not the most efficient way of doing this question. Yeah? So we've got to break it up. That would be the first thought people would be going with. However, that first section, area between the circle and the parabola, as I was saying, circle the x-axis. But there actually is a smarter way of doing this. It's a lot easier to work out the missing bit and then subtract it from a quarter of a circle. Because then the missing bit is just one integral, nice and neat. If I integrate from 0 to 1 of the parabola, subtract that from the circle, or a quarter of a circle, I know that's going to be my answer. So a quarter pi r squared minus that area under the parabola. So add 1 to the power over the power, and you eventually get that. Now remember that when you are doing integration, this is why diagrams can help. Because if it's a regular shape, you don't need to waste time integrating. If it's a triangle, I've got an area for a triangle. If it's a circle, I've got a formula for the area of a circle. Let's not waste time. Let's use those simple formulas we know. Where the integration is handy is when we get these unusual shapes that we don't know. Okay, here we go.